Good day, ECO235 students. We are in week 5 and we are still continuing with topic 2, which deals with nonlinear mathematical economic problems. We will be covering the topic of the Lagrange multiplier as well as partial elasticity this week. The prescribed readings for the Lagrange multiplier is chapter 8.4 of your prescribed textbook, and for knowledge enrichment purposes you can consult chapter 5.6 of the Jacques textbook. Now, the following example is just to recap what you've done in constraint optimization, particularly looking at consumption equilibrium. So here you have an example where you are given the information regarding the quantities of two goods, good X and good Y, and you're given the prices of the two goods as well as the income, and from that you can derive the budget constraint, and you're also given the utility function, which is an objective function. Now you are asked to calculate the maximum utility level subject to a budget constraint and to determine what combinations of good X and good Y would maximize utility. So based on what you learned last week, you would go ahead to find the marginal utilities of the two goods by using partial differential um, calculus, getting your first order partial derivatives with respect to X and Y respectively. And from that, your ratio of your marginal utilities gives you your marginal rate of substitution. And that is the slope of your indifference curve. Then you also had your price ratio, and here you also have your budget constraint. From that, you could see that at equilibrium, that is that point of tangency where your indifference curve touches your budget constraint at a point, and at that point, your slope of your indifference curve, which is your marginal rate of substitution, given by the ratio of your marginal utilities, it is equal to the slope of the budget constraint. So by setting those to equal, you could determine that optimal bundle mix, and you could then substitute that into the budget constraint to determine the combination of y and x, the quantities of y and x that would maximize utility, and then you could also determine what that utility would be. So this is the one method of solving your constraint optimization or consumption equilibrium problems. Now, another method is called the Lagrangian multiplier, and that is the focus of this week. Right, now we have an objective function, and that is this function over here. Now, an objective function defines the objective of the optimization. For example, are we planning to maximize utility, maximize output or profits of the firm, or minimize costs, for instance? And we also have constraints that pose some limit on the optimization. For example, a budget constraint if you're looking at utility. So to optimize this function over here, to optimize this function, subject to our budget constraint. Our budget constraint here, that symbol is phi, the letter, it's a Greek letter, and this tells me that phi is a function of two variables here. We have x and y, and m is the constant which is known, so that could be your income or the budget, and we want to optimize this function over here, so that could be your utility function, for instance, subject to this budget constraint. So the point is that we want to determine the numbers or values for x and y that in this case will maximize this objective function. So what is the optimal solution to this constraint problem? Now, the following steps must be followed. Firstly, you are going to have to define a new function, and this is the new function you are going to define, which we'll speak about in more depth in a moment. Next, you are going to have to find the three first order partial derivatives of this function, right? So that is with respect to x, y, and lambda. Then you are going to solve the simultaneous equations by setting those first order partial derivatives all equal to 0 so that you can solve for the three unknowns x, y, and lambda. So let's break down step 1 a bit further. So in step 1, you can see that we are in essence combining the objective function and the constraint, or budget constraint in this case, into one function, right? So first, the first thing you want to do is you want to rearrange the constraint such that that constant is m minus phi, right? So first rearrange the constraint in this form. So that can be done by taking this portion over to the right hand side and setting your left hand side equal to 0, right? Then of course the sign here would change, and then you're going to multiply that by some scalar called lambda, this Greek letter lambda. You're going to multiply it by that scalar lambda, and that is in fact your Lagrange multiplier, the scalar lambda. Then you're going to add this portion to your objective function, and in so doing you have defined a new function, and this function here is now called your Lagrangian function. So this function itself is your Lagrangian function, and that scalar lambda is your Lagrange multiplier. Now, in your second step, you are going to get your three first order partial derivatives and equate them equal to 0, right? So with the system of three simultaneous equations, you can then solve for x, y, and lambda, those three unknowns, and the optimal solution for this constraint problem. Now, lambda does have a particular meaning, but at this point in the course, you are not required to evaluate it. So we just require that you are able to determine what x and y is. So here we have an example, right? So you are asked to optimize an objective function subject to a budget constraint. Now, here is your objective function, your utility function. So if you want to optimize that, you want to maximize utility. And here is your budget constraint. So you can see that your budget or your income was 12, the price of good X was 1, and the price of good Y was 3 in this case. So rearrange it such that you have M minus what is on the left hand side. So if you take that over, of course, both these signs are going to change because you're setting this equal to 0 on the left hand side, right? So that is the first step in terms of defining the new function, rearranging this portion, your constraint, then multiplying it by the scalar lambda and adding that to your objective function. So let's have a look. There we have our new function. So our Lagrangian function here, g, is now a function of x, y, and lambda is equal to our objective function. Utility was just equal to x, y, so that is your objective function plus lambda. And you can see we've rearranged such that we have m minus x, so 12 minus x minus 3y. So of course you can just multiply out, so that's going to become plus 12 lambda. That negative times a positive gives you minus lambda x, and negative times a positive is going to give you minus 3 lambda y, right? So there is your new function. The next step is to get the three first order partial derivatives of this function. So you're going to get the partial derivative of this function g with respect to x, treating y and lambda as constant. So therefore, if I get my differentiate this, I'm just left with y. There is no x over there. Here I'm just left with minus lambda, and there is no x over there to differentiate. So my first order partial derivative with respect to x, treating y and lambda as constant, just leaves me with y minus lambda, and you can set it equal to 0. So by rearranging, we can have lambda is equal to y. Now you can get your next first order partial derivative of this function over here with respect to y, treating x and lambda as constant. So therefore you have, if you differentiate that, you're just going to be left with x. There's no y over there, no y over there. So here I'm just left with minus 3 lambda, and set that equal to 0. And again, you can rearrange, making lambda the subject of the formula, because remember, you want to solve simultaneously in the next step. So therefore, if I take that minus 3 lambda over, it would of course become positive. So therefore, it can become x over 3 is equal to lambda. Lastly, your last first order partial derivative of this function with respect to lambda, there's no lambda there. Here I've just got plus 12, and here I've got minus x and minus 3y if you get your first order partial derivative. And what do you notice? This here is just a restatement of what you had in brackets over there, your constraint. Right? So take note of that. It's that third equation is just a restatement of the constraint. So I just need to scroll down so we can see the rest of this problem. Right. So now you can see that we have lambda is equal to y and lambda is equal to x over 3. So surely we want to solve simultaneously. We can equate those two as is done over here. So now you have y is equal to x over 3, or you could say x is equal to 3y. So what are we going to do with this? What do you think? Well, you can substitute that into your third equation, right? If you were to go back, your third equation there was your first order partial derivative of that function with respect to lambda. You can now substitute that x is equal to 3y into there, which is what we have over there. And now, of course, that is going to be minus 3y minus 3y. That's going to be minus 6y. And if you take that over, it becomes positive. Hence, y is just going to be 12 divided by 6. That's 2. And hence, x was 3y, so x is 3 times 2, and that is 6. So therefore, your utility function is equal to the product of x, y. You have that combination of y and x, and it is equal to 12. So do you notice you've arrived at the same answer, although you've used a different method, the Lagrangian multiplier method? Right, so here is a home exercise. It is worked out fully. Please attempt this exercise on your own. Right, I'm going to do the second home exercise. So there we go. This is the second home exercise. Sorry, the first home exercise. I will go through the second. Right, so I have to pause the video now and start with the second part of this week's slides.